Alright, what I want to do is I want to go over the StateMachine PowerPoint here and talk about um, how to go about building one, but also the operation of a StateMachine. So let's take a look at our StateMachine PowerPoint. Now, this PowerPoint is with the phone number and the toll booth. It's the same PowerPoint. And it starts out, we're going to come across the table in here. The first table we're going to talk about is the more complicated circuit, the toll booth. And we're going to take a look at its state transition diagrams, and then we're going to look at the transition table. And then we're going to take a look at the more simpler phone number project that's a StateMachine. And if we take a look here, I want to move on here to StateMachine. Here we have a diagram, and it shows three areas here: input combinational logic, memory flip-flops, and output combinational logic. What's kind of neat about the StateMachines, it's the culmination of our year so far in digital electronics, in that the first semester we covered combinational logic, and you can see it on the input side and the output side over here. And then when we started our second half, we talked about asynchronous and synchronous counters. And in the middle here, we have something that looks like a synchronous counter. It's made out of flip-flops, and yes, it does count. It keeps track of what state we're in, and we're going to show you how that all works. So parts of the machine, and like I said, we have the combinational logic. And if we take a look at the combinational logic, I didn't turn on my editing here, so excuse me here for a second. I want to be able to edit this PowerPoint. Alright, so I'm going to get my little highlighter out. So what we have is, here we have our input logic. It's combinational logic, and we've designed that before, and we're going to show you how to do that. We have switches coming in, we have push buttons that come in, and we also feed back the states of the two flip-flops. So we also know what state we're in with the StateMachine, because obviously depending on what we want to do, we want to know where we're at. So let's take a look at the next slide. Memory, and yes, we're going to have flip-flops in here to keep track of it. The flip-flops are going to have a clock coming in. Clock will always be running to it, and based on the design that we do, first of all, the phone number will have a slow clock, and hopefully you'll see that when you build that. And the toll booth will need a little bit faster clock to run so that it can see the switch transitions and turn motors off or turn motors on. So. And then the last section of the StateMachine is the output logic right here. Now, what are we going to drive? We could drive 7-segment displays, we could turn LEDs on and off, and we could turn motors on and off, or reverse a motor, as in the case of the toll booth. And examples of StateMachines, everyday StateMachines, you can talk about these, pretty evident. I mean, our stop and go lights, that keypad on a garage door. When you take a look at the phone number one, you can kind of get an idea how the keypad number would work. And vending machines are StateMachines also. And our design method here, well, first of all, we have to create a state graph, and that's what we're going to go over in this PowerPoint. And we have to label our outputs and encode our outputs. And we have to create a state transition table, and we're going to talk about that. I'm going to do a different video on the state transition table, how to build one. And then we got to do a simplification of equations and design our circuit. First of all, this is what a state transition graph looks like. Yes, it does look a little complicated, but we're going to break it down and talk about it a little bit. This is actually the toll booth state diagram. It's the one that you're going to use in the activity when you build the toll booth. And if we take a look at it, we have three states. I'm sorry, we have four states. We start out with state 0, then we go to state 1, state 2, and state 3. So this table has 4 states, and each of the states are broken down like this. So first of all, we label the state, and we give it this design has 4 states. So in order to keep track of the 4 states, we're going to need 2 flip-flops, which for us, you know, in a regular counter would count 0, 1, 2, and 3. So that's why we have the 2 flip-flops. We're going to label them QA and QB. And state 0, they're both 0, like that. And based on this design here, they say there's some type of output. So down in this area, I noticed they put it right here inside the circle, but we're going to see it in our toll booth design. Down in this area here, you're going to have some output. Up here, we're going to have a transition arc, and as long as we're staying in state 0, boom, we're going to come right back to state 0. There's no transition to a new state yet because it's based on this input right here. And there's where the input variable goes. And I'm going to talk about this. A state, for example, state 0, really has 2 states. It has this transition arc where it's in the hold state, as it's labeled over here. And that's one of the states of a state. Then a state actually has a second state, and this comes into play when we build the transition table, and we call this one the next state or the transition arc. And based on some input changing, in this case X went from a 0 to a 1, it would cause us to go to the next state. Down here would be state 1. So that's the basic anatomy here of a state graph. And how do we keep track of what state we're in? Well, once again, we have 2 flip-flops. If you take a look at them, they have a clock that's fed into them. Like I said, the clock is continuously running. And if you look at this, it's kind of looks like a synchronous counter where the clock goes into both of them. And we're going to use D flip-flops on this, and we're going to show you how to design this logic that feeds the D input that's going to come up. That'll be in our another video that I'll put together. How do we build the table, and then how do we write equations from it. One nice thing about it is we can keep track of the states of the flip-flops right here. All right, so we keep track of the states of the 2 flip-flops. Now we put little LEDs on it or indicators, and this becomes very helpful when a student comes up to you and says, hey, my state machine doesn't work. Okay, well, first of all, let's see if it's moving from state to state. And these 2 little LEDs or indicators will be able to tell you that. So it's always good to add those on. I like to use those LEDs that are on board on the CMOD, tie 2 of those to these flip-flops, the Q outputs of the flip-flops. And here over here we show our states. So we start out state 0, QA and QB, the 2 flip-flops are in 0, 0. If we go to state 1, then they're a 0, 1. We go to state 2, they're a 1, 0. And when we hit state 3, the 2 flip-flops go to a 1 and a 1. And where do we go from state 3? We're going to find out as we start right back and go right back into state 0 again. So the state machine keeps running. But this is our state variables right here, QA and QB. And let's say, for example, if a 5th state was needed, well, what do you got to do if you had to count to 5? Well, we'd have to add another flip-flop, so you'd have to have a 3rd one. But fortunately, 2 designs we're going to use are going to be simple, and we only have two flip-flops for this. All right, here's our state machine. This example, we have 4 different states on it. And if you take a look at it, we have our input section up on top. And if we take a look, they got a nice little table down here. They lay out what the tables are. Now, hopefully, you took a look at the video on the toll booth before you started this, because it makes more sense by knowing what these switches do. So first of all, we have an open switch. This would be something, a push button, for example, an operator would push, and when he pushes it, the toll gate would open up. When we want to close it, we'd have a close switch. That's the CS one. When the toll booth is opening and it opens to its full limit, there'll be an an open limit switch. And when a toll booth is closing, when it hits the close point, when the gate's in the closed position, it'll hit the close limit switch. And those will be, those limit switches are those same switches we used on the copy jam circuit. We have an indicator. It says motor is, or we have a signal going out to the motor, an open signal, and we have a motor closed signal. These two signals feed the H bridge, and one opens the gate, one closes the gate. And it's a little bit different than the copy jam. Copy jam, we turn the motor on, turn the motor off. A little later on, I'm going to go over the activity, and in the activity I'm going to show you that the H bridge actually can reverse the direction of the motor. Then down here we have two LEDs, a gate open LED when the gate's fully open, and then we have an LED that indicates the gate's closed. So there's our key to what all these little letters mean up here. And like I said, if you haven't gone over the video on how the toll booth works and operates, it might help before we get started in here. I want to just take a look at my next slide here. Nope, I don't want to go there yet. So let's look at this slide right here. We're in state 0. We can tell that by the two flip-flops, QA and QB. And we're going to stay in state 0. We're going to constantly stay in state 0, going around and around. Let's see what else we know about state 0. If we take a look down here, the gate is closed because the gate closed LED is on. And our open switch, nobody has pushed the open switch. The open switch equals 0 right now. We don't care about the closed switch, we don't care about the open limit switch, and we don't care about the closed limit switch right now. Those are all don't cares. If you remember the X's from when we did K-mapping, and you're going to see how the X's are going to help us out when we actually write equations from the transition table. So we're sitting here waiting, and what we're waiting for is somebody to push the open switch because the gate is closed right now. And if you take a look over here, when somebody does push the open switch, it goes to a 1. Then we're going to make this transition. Remember, we're still in stage 0 until we have actually got down here to state 1. So this is one part of state 0. And this is that second part of state 0, that transition arc. So this is the one where it stays in the same state constantly until some action occurs. This is the action, the switch opening. Now we're going down to state 1. All right, let's take a look at what's going on in state 1. Let's look at our outputs. The gate open LED is off. The gate closed LED is off. Motor closed signal is at 0, but motor open is on. So motor open, the gate's opening. So the gate is starting to go up. And we're going to sit here in state 1. We're going to go around in state 1. And we're, as long as the open limit switch is equal to 0. That means we haven't hit that open limit switch at the top here. So the gate's in motion. The motor's running. We can see our state of our two flip-flops are 0, 1. And what we're waiting for is when the open limit switch happens. When the open limit switch occurs, when we get this open limit switch equal to 1, all of a sudden we're going to make a transition. We're still in state 1. This is the second part of state 1. Remember, the first part of state 1 is this, while we're waiting for the motors running, the open limit switch is up. So the open limit switch is equal to 1. That gives us this transition down here to state number 2. And as soon as we hit state number 2, our two flip-flops change to 1, 0. Our gate open LED turns on, and if you notice, our motor open is equal to 0, and of course our motor closed is equal to 0 too. So our two motor controls are turned off. Motor's not running. And what we're doing is we're sitting in this transition right here. We're in state 2, the gate's open, and we're constantly going around in a circle. The close switch, close switch or close push button, maybe I should refer to it as a push button, is equal to 0. Nobody's pushing it right now. So we're in state 2, and we're staying in part 1 of state 2 right here. Constantly circling, until someone hits the close switch. So the close switch is hit. Now we go into part 2 of state 2, and we make this transition over here to state 3. And as soon as we hit state 3, we see the motor closed is turned on. Gate open LED is turned off. Remember, it was on down here, so it turned off. Our 2 states go to 1, 1, which is state 3, or 2 state flip-flops. And the gate now, the motor's running and the gate is coming down. And the gate will continue to come down as we transition through here, as we're going, constantly transitioning. This is one part of state 3. And we're watching for the closed limit switch. You notice we have the X's in the others. We don't care about them. And we're waiting for the closed limit switch to hit. Motors closing, gates going down. As soon as we hit the closed limit switch, we go to part 2 of state 3, which is this transition arc. And what happens is it brings us back over here right away. And what we do is we turn the motor off, the closed motor's off. Our 2 states go back to 0. Gate closed is equal to 1. And now we're sitting here waiting once again for the open switch to open. So a couple of things to take away from this. We got our inputs up here. We got our outputs down here. We've got our transition, what allows us to transition to the next state. We got our number of states here. But the important thing to remember is, as we go to the building of the state transition table, is there's 2 parts to a state. There's this part right here where we're in idle mode in the state, where we're in the state, staying in the state. And then part 2 of a state is when we actually get some input that makes us change or transition. So, all right, so that's all I was going to cover on this video. The next video is going to talk about how do we build a transition table from this. So